Okay, this is the last chapter on uh, solar energy, and this will cover photovoltaics, chapter 9. So this is an intro. Photovoltaics, as you probably all know, refers to direct generation of electricity by solar irradiation. So you have a solar panel, it absorbs a certain amount of energy from the solar rays and then converts it into electricity. So some things relative to it, atomic theory and semiconductor theory are good places to start in order to examine how photovoltaic cells operate. So in an atom, the number of protons is equal to the number of electrons, and that number is the atomic number of the element. Same basic concept that we went over when we did nuclear energy. In silicon, the valence bond is partially filled and contains 4 electrons. It must contain 8 electrons to be filled. So, if electrons in an unfilled valence bond are lightly bound, they may attach themselves to a neighboring atom, which gives that atom a negative charge, resulting in the donor atoms becoming a positively charged ion. So electrons in a valence band can become so energetic that they jump into a band that is far removed from the nucleus. This remote band is called the conduction band. So the difference in energy between the electron in a valence band and one in the conduction band is called the band gap energy. So electrons in the conduction band require only a small amount of energy to move away from the atom, and this is responsible for heat and electrical conduction. Band gap energies are usually expressed in electron volts. So insulators are materials whose atoms possess full valence bonds and have high band gap energies. Conductors are materials whose atoms have relatively empty valence bands. And materials whose atoms have relatively full valence bands are semiconductors, with band gap energies less than 3 electron volts. Table 9.1 in your book is a table that shows different representative photovoltaic material band gap energies, namely silicon, cadmium telluride, cadmium sulfide, copper indium diselenide, and so forth and so on. All of them have band gap energies less than 3 electron volts. Silicon is an example of a semiconductor, 4 electrons in the valence band. Pure silicon is called an intrinsic semiconductor, but if a small amount of impurities, usually called a dopant, is combined with the pure silicon, an extrinsic semiconductor results. So you have 2 types. You have an N-type semiconductor, which results if the dopant has more electrons in a valence band than the base material. An N-type semiconductor seems to have an excess of electrons, even though the semiconductor is electrically neutral. A P-type, the other type of semiconductor, results if the dopant has fewer electrons in the valence band than the base material. The P-type semiconductor appears to have a deficit of electrons, or an excess of holes, although it's electrically neutral. So the reason for doping a pure semiconductor such as silicon is that a junction formed with N-type and P-type semiconductors enhances the flow of electrons. Here, for example, you have a PV cell. Photovoltaic cell is shown as a PN junction with an incident proton. An external load is connected. If the incident proton is energetic enough to dislodge a valence electron, the electron will jump to the conduction band and initiate a current flow. For an electron to be forced from the valence band to the conduction band, the electron must possess at least the band gap energy. So the energy of a photon is given by this equation, where h is Planck's constant and nu is determined as the speed of light divided by the wavelength. So let's say, for example, I want you to determine the wavelength of light that corresponds to the band gap energy of silicon, 1.11 electron volts. So if you were to take that equation and solve for lambda, Planck's constant times the speed of light, over the band gap energy, multiplied by the speed of light. Divided by the band gap energy, where there is 1.16 times 10 to the negative 19 joules per electron volt. In this case, you get lambda as 1.12 micrometers. So again, that is the wavelength that corresponds to the band gap energy of silicon. So how does that relate to photovoltaic cells? Well, that example problem has important implications for the operation and efficiency of photovoltaic devices. Photons with a wavelength greater than 1.12 micrometers contain insufficient energy to dislodge a valence electron in silicon. Hence, protons with wavelengths greater than 1.12 microns will induce no photovoltaic effect in silicon. But on the other hand, protons with a wavelength less than 1.12 micrometers possess more energy than is required to dislodge a valence electron. However, a single photon can dislodge only a single valence electron, and the difference between the band gap energy and the photon energy is absorbed as heat by the PV device. So here you can see a graph in figure 9.3 in your book. This figure is useful in delineating the behavior of a photovoltaic device exposed to solar radiation. Y-axis you have relative intensity, x-axis you have wavelength. Here is the threshold. Anything less than 1.12 microns has enough energy to dislodge a valence electron, where anything greater does not. And that is for the case of silicon. If the energy required to dislodge, the energy at 1.12 micrometers represents the energy required to dislodge a silicon valence electron, then the equations we just went over can be converted to a ratio form to express that portion of the energy required to dislodge a valence electron for a wavelength lower than 1.12 micrometers. Thus, the smaller the wavelength, the greater the excess energy of the photon. The generally low efficiencies of photovoltaic devices are attributable to this principle and to additional conversion of inefficiencies associated with proton wavelengths less than those corresponding to the exact band gap energy. So, Table 9.2, for example, shows the theoretical and measured efficiencies of photovoltaic cells. So there are several photovoltaic materials. Taking the example of silicon, it has a theoretical operational percentage of 24%, but the measured was 18, and all the rest have ones lower. Figure 9.4 in your book looks at the history of photovoltaic efficiencies given by the NREL. As you can tell, 1975 we had efficiencies more or less below 12%. Whereas close to 2010, those efficiencies were starting to approach 40%. So one strategy used to overcome the relatively low conversion efficiencies of solar cells is to provide more than a single junction. That is, to fabricate two or more junctions, one above the other. Over the last decade, these multi-junction photovoltaic cells have shown impressive increases in conversion efficiencies. So figure 9.5 shows the current density at a p-n junction. Here we have the current density, which is basically the current per area, and J sub r would be the current going from the n-type to the p-type semiconductor, and J sub 0 would be going from the p-type to the n-type. Figure 9.6 shows the equivalent of a photovoltaic cell circuit. You can get that the current coming from, the current density going from the n-type to the p-type conductor can be given by the equation that I just circled, where E is the charge of one electron, and K is Boltzmann's constant. So here we have that the junction density, J, would be the current density going from N-type to P-type minus that going from the P-type to the N-type. So that gives us the following. And the junction can be the current coming J sub S minus the junction. Sorry, that's the J sub. Excuse me. J sub L. So that would be the actual load. So the actual load current would be what we would call the short circuit current minus the junction current. If the cell is short-circuited, that means that the resistance for the load is 0. Again, this side of the photovoltaic cell circuit would be the actual electric work that's being done. So if there is no resistance, that means that the short circuit current would be equal to the load circuit current. And that requires the voltage to be 0. If the circuit is open, that means that the load current is 0, and the output of the cell is directed through the junction. Under these conditions, the voltage is called the open circuit voltage, or V sub OC. The performance of a photovoltaic cell is typically described using the short circuit current and the open circuit voltage. And these are the equations that are used to determine the open circuit voltage and the load current. So given the open circuit voltage and temperature, the equation can be solved for the ratio. A typical value of the open circuit voltage is 0.6 volts for a single solar cell. The ratio is quite large. Dividing the prior equation from the prior slide by the by J sub S yields an expression for the load current density to short circuit current density ratio. By using that equation 910, and a specified value of the open circuit voltage, the current density versus voltage relationship can be determined. The power density delivered to the load is the load currency, or the load current density, times the voltage drop across the load. So this figure 9.7 represents the current density ratio and power ratio versus voltage. Figure 9.7 presents, for an open circuit voltage of 0.6 volts and a temperature of 300 Kelvin, the variations of the normalized power as a function of the voltage. The power is normalized with the maximum power to the load, which occurs at a voltage of 0.5 volts. So you can see how the current density stays the same until the load starts, and then eventually, as the load voltage increases, the current density starts to decrease after this threshold. You can see the power ratio increase as the voltage increases to a certain maximum, and then eventually it goes and decreases down until you hit the open circuit voltage. Not surprisingly, the higher the solar irradiation, the higher the power output of a photovoltaic cell. Consider as shown in the figure the effect of irradiation on the performance of a solar cell. As the solar irradiation increases, the open circuit voltage increases slightly, but the load current is almost directly proportional to the solar irradiation. The maximum power to the load is almost directly proportional to the solar irradiation incident on the cell itself. So let's look at the photovoltaic components. The fundamental element is the individual photovoltaic cell. Individual cells are assimilated into modules, and modules are assembled into arrays, which are integrated into systems with a wide range of components. This figure 9.9 schematically illustrates the sequence. So you have a cell, which are aligned in series that form a module, and each module is combined to make an array. Figure 9.10 in your book reproduces some of the information from a company's site, Photowatt, particularly for their Photowatt model cell 125. The first portion of the figure produces a visual image of the cell, as well as presenting information on the size of materials used and some construction details. The table in the middle segment of the figure delineates the open circuit voltage and short circuit current, and the voltage, current, power, and efficiency at maximum power for different classes of the solar cell. The Photowatt IV curve is illustrated as the last portion of the figure. The IV curve is similar to the theoretical one of figure 9.7, implying that the simple model is realistic and useful. So here you have the different classes, the open circuit voltage, the current, and then certain performance parameters. An examination of the numbers confirms that the appreciable power and voltage are to be attained more than a single cell being needed. Modules are constructed by placing photovoltaic cells in series and parallel arrangements. Series and parallel configurations of solar cells follow the same rules as series and parallel DC circuits. For identical components placed in a series arrangement, the voltages add a constant current, and for identical components placed in parallel, the currents add at constant voltage. So, figure 9.11 shows the behavior of cells in series and parallel. So, for example, figure A shows two identical cells in series, and figure B shows two identical cells in parallel. For cells in series, figure A, the voltages add at constant values of the current, hence placing cells in series results in increased voltage. The cells in parallel, figure B, result in increased current. So looking at an example problem, let's go ahead and try to see how to arrange solar cells to meet specific needs. I have a photowatt class AH photovoltaic cells are to be arranged to provide an output of 12 volts and a power of 120 watts. Recommend an arrangement that meets the specifications. So in this case, I want the power to be 120 watts. So if I go back, I need to find the amount of power per cell. So if I do that, I can go ahead and go back a few slides, looking under photovoltaic, the class AH. I should see that this particular cell produces 2.53 watts per cell. Right, so I want to be able to use that to find the number of cells that I need. So first off, the number of cells is going to be the total power that I need divided by the wattage per cell. So I need, in this case, 47.4 cells. Now to get the voltage that I need to arrange a certain number of cells in series. So I need to go back and I need to look at the voltage that I get per cell. It so happens that the operational voltage that I get in order to be able to produce 2.53 watts is 0.49 volts per cell. So, in order to get the number of cells in series, I take my desired voltage divided by the voltage per cell, and I get 24.3 total cells in order to get a minimum of 12 volts. So if I'm going to do this, it looks like I'm going to need 2 rows of 25 cells. So that would be the arrangement that I need for this particular photovoltaic cell in order to produce 12 volts and 120 watts. Okay, I hope that's pretty clear. Now, there's one other interesting example problem that I want to use more as an illustration rather than actually going through it. This slide also looks at some performance factors for other voltaic cell models. But the example problem I just wanted to illustrate is example 9.3. This particular problem says, estimate the annual kilowatt-hour production of one BP E160 module. That would be the module from the prior slide. I'm sorry, that's actually not true. It's not on this slide. It's on. It should be on another chart in the book. I apologize. I thought that particular slide had information on that particular cell. But in any case, I'll move on and talk about the problem itself. So the production of one module in Meridian, Mississippi. Examine 2 cases: a constant tilt at the latitude angle and a 2-axis rotation. So this is looking at taking a photovoltaic cell and following the path of the sun either on 1 or 2 axes. So like we did in prior chapters, where you look at the amount of days in a month, and then the monthly average conditions from NREL, where you get some solar, obtain some solar and weather data, looking at the kilowatt hour per meter squared day over the course of the month. You can actually get to a point that allows you to be able to figure out if you were to follow the sun either on a fixed tilt or on a 2-axis rotation. So I'm sorry, this is a constant tilt at the latitude angle. I originally said that this is rotated on 1 axis. That's not true. I need to backpedal and say that the problem itself wanted to analyze either the annual kilowatt-hour production at a constant tilt or at the latitude angle or a 2-axis rotation. As you can see, especially during the summer months and spring months, you get a lot more solar energy by tracking the sun than you would at a fixed angle. And then, of course, modules such as those discussed in this prior example problem are assembled into arrays utilizing the same series and parallel principles used for combining cells into modules. So this particular figure is an example of a PV array, and the array is rated at 236 kilowatts, and it was made by American Energy Technologies. That pretty much ends this chapter. I know that some of this content can be rather confusing, especially when it has to deal with principles of electricity generation, which is not exactly lined up with what you've done in prior classes. But what I really want you to understand from this chapter is just the basic concepts on how photovoltaic cells operate, and then some basic calculations in using photovoltaic cell data and being able to come up with some simple arrangements in order to meet power and voltage needs. That ends this chapter. Of course, if you have any questions, you can give me an email. Like I said, I'll do my best to try to respond as quickly as possible. Thank you very much.